In the previous lecture, we have started to deal with a new chapter in waves and oscillation, and that was actually the superposition of harmonic oscillations. And in fact, in that very lecture, you have seen just a brief introduction regarding this superposition of harmonic oscillations. Now, from today, we will see the actual problem of this chapter. And first of all, we are going to see the superposition of two harmonic oscillations, only two. But later on, we will also see the superposition of more than two simple harmonic oscillations. And when you talk about the superposition of two simple harmonic oscillations, again there will be actually two cases. First of all, we will consider the superposition of two collinear simple harmonic oscillations. Okay? And after that, we will see the concept of the superposition of two simple harmonic oscillations acting at right angle. Actually, when we will talk about the superposition of two simple harmonic oscillations acting at right angle, a very important concept of Lissajous figures will come. Okay? And that is our core aim. In fact, again, when you talk about the superposition of two collinear simple harmonic oscillations, actually, again, there will be two cases. First of all, we will see the superposition of two collinear simple harmonic vibrations of equal frequencies. And after that, we will see the same problem when the frequencies of the two harmonic oscillations will be different. That will actually differ from one another slightly. And then you will see a very important concept of bits come into the picture. Okay? But this is the most simplest form of superposition problem, and this is regarding the superposition of two collinear simple harmonic motions having equal frequencies. Okay? So now let us see these figures. I have shown in this first figure that there is, let us consider a particle or an oscillator, you can say, which is acted upon by a restoring force F1. F1 is the restoring force acting on our particle or the oscillator. And you know, whenever a restoring force acts on a particle, the particle executes linear simple harmonic motion. So we consider that under this restoring force F1, our particle or the oscillator is executing SHM on this straight line, which is, let us say, x-axis. Okay? And you can see this O is actually the equilibrium position. And at any moment t, we consider that this x1 is the displacement of the oscillator from its equilibrium position. Okay? So if you want to describe this simple harmonic motion, what will be the solution of the equation of simple harmonic motion, or you can say also what will be the equation that will represent this motion. You have learnt already in first chapter that such a simple harmonic motion is expressed by this equation x1 of t equal to a1 times cosine of omega t plus phi 1. Actually here, you know, x1 of t, this is displacement of the oscillator at any moment t. And a1, which is the maximum value of x1, that is called amplitude of this oscillation. Okay? And here omega, you know, this is the angular or cyclic frequency of this motion. And phi 1 is called phase constant or angle of epoch. Okay? As you have seen earlier that instead of this cosine function, you may also write the sine function. Okay? But I have taken here the cosine function. Now, Let us remove this force F1 acting on this particle and apply another restoring force, let us say F2, on the same particle. Now, under this restoring force F2, we consider that the particle again executes SHM along the x-axis. And I have shown in this second figure that this x2 is the displacement of our particle at any time t from the equilibrium position when it executes SHM under the another restoring force F2. Okay? So this motion will be described by the equation x2 of t equal to a2 times cosine of omega t plus phi 2. Here a2 is amplitude of this oscillation and phi 2 is the phase constant. Okay? And you can see that I have considered the angular frequency of this second SHM omega 2. So as I have told you in this problem in earlier, that we will see the superposition of two simple harmonic motions whose frequencies are equal, although their amplitudes will be different, phase constants will be different, but frequencies are same. Okay? Now let us consider that both of these restoring forces F1 and F2 are applied on this oscillator together simultaneously, as you can see in this third figure. So now the restoring force acting on this oscillator is F1 plus F2, and we consider that under this resultant force our particle or oscillator again executes SHM, and at any moment t its displacement from its equilibrium position is x, as you can see in this third figure. Okay? Here our aim is to know, if you know x1 and x2, how you can find x. Actually, as you have seen in the introductory lecture, the principle of superposition. So applying the principle of superposition, you can easily find the resultant motion. And what is this superposition principle? You know, according to the superposition principle, the resultant displacement of this particle will be simply the algebraic sum of the displacements x1 and x2 which were taking place under the restoring force F1 and F2. When F1 was acting alone, then displacement was x1. When F2 was acting alone, then displacement was x2. But when F1 and F2 act together, then according to superposition principle, the resultant motion will be given by x of t equal to x1 of t plus x2 of t. Actually, this problem can be solved by different methods. I have here actually discussed only two methods, but there may be a third method which we will see later on. So there are two methods to find the resulting motion after the superposition of these two simple harmonic oscillations with same frequencies but different amplitude and different phase constant. The first method is called analytical method, or you can also say it mathematical method. And the another method that is called vector method, or that is also known as geometrical method. Okay? So as I have told you that in accordance with superposition principle, the resultant displacement will be simply x1 of t plus x2 of t. Since we have considered that both x1 and x2 are in same direction, therefore the algebraic sum of x1 x2 will be simply x1 of t plus x2 of t, and that will be equal to the resultant displacement x of t of the oscillator. But you have seen that x1 of t is equal to a1 times cosine of omega t plus phi 1, and x2 of t is a2 times cosine of omega t plus phi 2. So I have substituted these. Now you can expand cos omega t plus phi 1 and cos omega t plus phi 2 on the basis of the trigonometric formula for cos A plus B. You know cos A plus B is what? That is cos A times cos B minus sin A times sin B. So utilizing that very formula, you can say that the first term is A1 times cos omega t times cos phi 1 minus sin omega t times sin phi 1. And the second term will be A2 times cos omega t times cos phi 2 minus sin omega t sin phi 2. Okay. Now let us arrange the terms. You can see in the first term inside the first square bracket and inside the second square bracket, this cos omega t term is content. So you can take this cos omega t as a common factor, and the remaining terms will be A1 times cos phi 1 plus A2 times cos phi 2. Now consider this second term. See this second term. You can see in this second term we can take sin omega t as a common factor, and so this will be minus A1 times sin phi 1 plus A2 times sin phi 2 times sin omega t. Okay. Now let us put A1 sin phi 1 plus A2 sin phi 2 is equal to A sin delta, and A1 cos phi 1 plus A2 cos phi 2 is equal to A cos delta. We consider it. Here actually A and delta both are unknown. We have actually assumed. So our aim will be actually to find or to determine the values of A and delta. Okay. So now you can easily see how we can find the value of A and delta. If your aim is to find the value of A, you can see this equation 4 and 5. When you will square equation 4 and 5 and simply add after squaring, you will get the value of A. So let us square equation 4 and 5 and after that add those. So doing this, you can see that this, okay. But first of all, we will actually put the values of this factor A1 cos phi 1 plus A2 cos phi 2 and A1 sin phi 1 plus A2 sin phi 2. For this, we will substitute actually A cos delta and A sin delta. So after using equation 4 and 5 in 3, what will be our result? Our result will be x of t equal to A times cos omega t times cos delta minus sin omega t sin delta. Okay. But again, from the formula for cos A plus B, you can write cos omega t plus delta instead of the expression inside this square bracket. So the resulting motion is described by the equation x of t equal to A cos omega t plus delta. You can see the form of this equation. This equation also represents a simple harmonic motion with the same frequency omega but different amplitude A and different phase constant delta. Here actually A is different from both A1 and A2 and delta is different from both phi 1 and phi 2. Okay. So this is the equation of motion of the resulting SHM. So after superposition of these two SHMs of equal frequencies, we get again a SHM along the x-axis. But as you know, this A and delta we have assumed arbitrarily. These are not known. So now our task is to find the value of this A and delta. You can actually easily see that this A and how this A and delta can be found. As I have told you, if you will square equation 4 and 5 and add, you will get the value of A square or A. So you can see when we will square A square times sin square delta plus cos square delta, that will be equal to A1 square plus. Now let us see, when you will square these two, the first term in this equation 4 will be a1 square sine square phi 1, and in this after squaring equation 5 that will be a1 square cos square phi 1. So you can take a1 square as a common factor, and the remaining term will be sine square phi 1 plus cos square phi 1. Then there will be a2 square sine square phi 2 plus a2 square cos square phi 2. Again you can take a2 square as a common factor, and after that there will be a term 2a1 a2 sine phi 1 times sine phi 2 and 2a1 a2 cos phi 1 times cos phi 2. And so you can take 2a1 a2 as a common factor. So now you can see our result is a1 square times sine phi square phi 1 plus cos square phi 1 plus a2 square sine square phi 2 plus cos square, and the third term will be 2a1 a2 cos phi 1 times cos phi 2 plus sine phi 1 times sine phi 2. Okay. Now you know this sine square phi 1 plus cos square phi 1, sine square phi 2 plus cos square phi 2, both will be equal to 1. So in RHS, the first term is a1 square and the second is a2 square. And again, see the expression cos phi 1 times cos phi 2 plus sine phi 1 times sine phi 2. What is this? This is equal to cosine of phi 2 minus phi 1 or phi 1 minus phi 2. You know cos minus theta is equal to cos theta. So you can also write cos phi 1 minus phi 2, okay, or phi 2 minus phi 1, both. So in this way we have obtained the value of a square, and therefore a is equal to a square root of a1 square plus a2 square plus 2a1 a2 cosine of phi 2 minus phi 1. So now you can see from this equation that we can find the amplitude of the resulting SHM if you know the amplitude of the individual SHMs and also the phase constant of the individual SHM. So using this formula you can easily find the value of A. Actually it is also obvious from this figure that if you construct a right angle triangle and you take its base equal to this much and its height equal to this much, then its hypotenuse will be A. You can see this is equal to in fact A sine delta, and this is equal to A cos delta, and when you will square and add, that will be equal to A square. So this triangle actually satisfied that condition. Okay. So in this way we have obtained the amplitude of the resulting motion. Now the another unknown is delta, which is actually the phase constant of the resulting motion. Now to obtain the value of delta, you can see these two equations again. When you will divide this equation 4 by 5, then this delta will be removed, will be omitted, and you will this A will be removed and delta will be obtained. Sin delta by cos delta, that will be simply equal to tan delta. Okay. And so tan delta will be equal to this much. This is A1 sin phi 1 plus A2 sin phi 2 over A1 cos phi 1 plus A2 cos phi 2. Again you can see this phase constant delta can be obtained when we know the amplitudes and the phase constant of the two individual simple harmonic motions. Okay. So this was the analytical method, how we can obtain the resulting motion when two simple harmonic motions acting in same direction get superposed and their frequencies are equal. Okay. And you can see that actually as a conclusion we can say that the resultant effect of two collinear simple harmonic motions of equal frequencies is also a simple harmonic motion of the same frequency, but having amplitude and phase constant given by this equation A2 and equation A3. Okay. So I hope this was a very simple concept, and definitely you have understand these things clearly. Now we are going to see another method for the same problem. This is called actually the geometrical method. Actually here vector addition of amplitude will be considered. In fact, you have seen in my previous video that the SHM can be represented by a rotating vector. SHM is just visualized as a rotating vector. And this rotating vector representation of simple harmonic motion provides a very simple geometrical method of obtaining the resultant of two simple harmonic motions with equal frequencies. Okay? And for this, let us see this figure. In this figure, you can see that I have considered a vector OP1. See this, OP1. This OP1 be a rotating vector of length A1, okay, which is actually the amplitude of the first oscillation. And this vector makes an angle, you can see this angle, omega t plus phi 1, omega t plus phi 1, or you can say that angle P1 O N1 or X. This is equal to omega t plus phi 1. This is the angle made by vector OP1 with x-axis, okay, at any time t, because this angle is time dependent. So this is the angle made by the rotating vector OP1 with x-axis at any time t, okay. And here omega, is the angular frequency of oscillation or the angular velocity of this rotating vector, you can say. And phi 1 is the phase constant. Okay. Now you can see when you will draw a perpendicular from this P1 to x-axis, the perpendicular falls at N1. And I have shown in this figure that this ON1 is equal to x1. What is this x1? This is nothing, this is simply the projection or the component of vector A1 or OP1 along x-axis. So x1, which is actually the displacement of our first oscillator, that is simply the projection of the amplitude of the first oscillator, okay, in x direction, okay. And from figure you can see that this x1 will be equal to what? Since it is projection of A1 along x-axis and A1 makes an angle omega t plus phi 1 with x-axis, so x1 will be equal to A1 cos omega t plus phi 1. And this equation actually represents the first simple harmonic motion. Okay. Similarly, you can also see that I have assumed this vector OP2. This is another rotating vector and its length is A2, which is actually the amplitude of the second simple harmonic motion. And this vector A2 or OP2, which is a rotating vector, that actually makes this angle omega t plus phi 2, that is angle P2ON is equal to omega t plus phi 2, which is the angle made by this rotating vector A2 with x-axis at any time t. Okay. Now, taking OP1 and OP2, if you will construct a parallelogram, which you can see in this figure, that parallelogram is OP1, PP2. This is the parallelogram constructed by taking OP1 and OP2 as the adjacent side. Now, definitely in your lower classes you have studied the parallelogram law of vector addition. When we represent the two adjacent sides of a parallelogram by two vectors, then the resultant of those two vectors is represented by the diagonal of the parallelogram which passes through the point of intersection of those two adjacent sides. So this diagonal OP, which has a length of A, represents the resultant vector, resultant of A1 and A2. Okay, and we consider that this resultant A makes an angle beta with this OP1 or vector this. Now, before that you can see if OP2 is another rotating vector, and when you will draw a perpendicular, let us say P2 and 2 on x-axis, then you can see that this O and 2, this is equal to x2, which is actually the projection of this A2 along x-axis. And what will be that projection? That will be A2 times cosine of omega t plus phi 2, because this vector A2 makes an angle omega t plus phi 2 with x-axis at any time t. Okay. So now you can see how we can find the resultant A. This is very easy to find. If you know the triangle law of addition or the parallelogram law of addition, if there are two vectors A and B and the angle between those two vectors is theta, then the resultant R is given as a square root of A square plus B square plus 2AB cos theta. Okay. Here, what will be the angle between vector A1 and A2? You can see. Actually, if phi is the angle between vector A1 and A2 from the geometry of this figure, you can see this will be equal to omega t plus phi 2 minus omega t plus phi 1. Because angle will be P2OP1, and that P2OP1 will be equal to P2ON minus P1ON. Okay. So omega t will cancel and this will be simply equal to phi 2 minus phi 1. So angle between vector A1 and A2 is phi 2 minus phi 1. So now using the formula for vector addition of two vectors, you can see that the resultant A is equal to a square root of A1 square plus A2 square plus 2A1 A2 cos phi 2 minus phi 1. Okay. Instead of this phi 2 minus phi 1, you can write this phi. Actually, what I have explained, I have mentioned it here. You can see that this ON1, which is x1, this is projection of A1 on x-axis, and this is A1 cos omega t plus phi 1. And actually, this is displacement of the oscillator in time t in x direction. Similarly, ON2, this is actually x2, which is projection of A2 on x-axis, and this is given as A2 cos cosine of omega t plus phi 2. And this is displacement of the oscillator in time t in x direction. Okay. Now from the law of vector addition, you know OP will be equal to OP1 plus OP2, or A is equal to A1 plus A2. Okay. And as I have told you that if you consider that phi is the angle between vectors A1 and A2, then from the geometry of figure you can see this is equal to omega t plus phi 2 minus omega t plus phi 1, which is actually phi 2 minus phi 1. And so applying the formula for getting the resultant of two vectors, you can say that the magnitude of the resultant amplitude is equal to a square root of A1 square plus A2 square plus 2A1 A2 cosine of phi 2 minus phi 1. Okay. So in this way we have obtained the amplitude of the resultant motion. Now actually our aim is to find the phase constant of the resulting motion. Okay. Now the total phase of the resulting motion, you know, omega t plus phi 1, this is phase of first motion at time t, and this is the angle made by A1 with x-axis. Similarly, you can see omega t plus phi 2, which is angle made by vector A2 with x-axis at time t. This is the total phase of second SHM. Similarly, if A is the resultant amplitude, then the angle made by this vector A with x-axis, this will be the total phase of the resulting motion. Total phase. Now, this total phase of the resulting motion we can consider this is angle PON, and that is equal to omega t plus delta. Here actually delta is the phase constant of this resulting motion. Okay. Now let us see a simplified figure on the basis of triangle law of addition. Here in this figure I have again shown that this OP1 vector represents A1 and this P1P represents A2. Okay. And you know that according to triangle law of addition, then this OP will represent the resultant A. Okay. Now, the angle between vector A1 and A2, you have seen earlier, that angle is phi and that is equal to phi 2 minus phi 1. So, this exterior angle which represents actually the angle between vector A1 and A2. Definitely you have an idea that this interior angle is not angle between vector A1 and A2. Whenever you talk about the angle between two vectors, you have to see the angle of divergence. Actually A1 is directed in this direction and A2 in this direction. So this exterior angle is the angle between these two vectors and that is equal to phi 2 minus phi 1. Now you can see from this figure, if you will draw a perpendicular, let us say this PP3, then from the right angle triangle P1 P3, this P3 will be A2 sin phi and P1 P3 will be A2 cos phi. It is obvious from the geometry of figure. Okay. And now from this figure you can easily find the value of A again. You can see from this right angle triangle, if you want to find the value of OP, what will be that OP? That OP will be a square root of OP3 plus OP3 square plus PP3 square whole to the power half. But see the figure, OP3 this will be equal to A1 plus A2 cos phi. So this is A1 plus A2 cos phi whole square and plus A2 square sin square phi and whole to the power half. And this OP is actually A. So simplifying this, you will again get this result. Here phi has been written at the place of phi 2 minus phi 1. Okay. Now you can see the omega t plus delta, this represents angle POX. Okay. This is angle POX. Or here according to this figure, this will be PON or POX, you can say. Okay. And this angle is simply the sum of beta plus omega t plus phi 1. So you can see omega t plus delta, which is the total phase of resulting motion, that will be equal to omega t plus phi 1 plus beta. Okay. Now this omega t will cancel out and therefore delta is equal to beta plus phi 1. So tan delta will be equal to tan beta plus phi 1. And you know from the formula of trigonometry that this tan beta plus phi 1 can be written as tan beta plus tan phi 1 over 1 plus tan beta times tan phi 1. Okay. But what will be tan beta? See this figure. This is a right angle triangle. You can see POP3. And from this figure, tan beta will be equal to PP3 divided by OP3, PP3 by OP3. But PP3, you know, that is equal to A2 sine phi, but phi instead of phi I have written phi 2 minus phi 1, and divided by OP3, which is OP1 plus P1 P3. OP1 is A1 and P1 P3 is A2 cos phi. And instead of cos phi, you can write cos phi 2 minus phi 1. So in this way, we can obtain the value of tan beta. Now, when you will put this value of tan beta in this equation and you will simplify, there will be a lot of algebra. I have not done here, but you can do it. So let us put this value of tan beta here, and after that you must simplify the equation. After simplification, you will see that tan delta is equal to A1 sin phi 1 plus A2 sin phi 2 over A1 cos phi 1 plus A2 cos phi 2. And you can see this result is same as that we have obtained in our first analytical method. So in this way, by these two methods, you can easily find the resultant of two simple harmonic motions of equal frequencies acting on the same line in same direction. Okay. This was a very simple lecture, and I hope definitely you have understand each and every aspect clearly. Okay. Now in our second lecture, we will see the idea of the superposition of two simple harmonic motions of different frequencies, but they are collinear. Actually, from that we will get the idea of bits, which is a very important concept in particularly in case of sound wave. Okay, thank you very much.